All right, perfect. Well, thanks everybody. Welcome to, I guess this is August 2024, our Govys seminar, and we're really happy to have David Corliss with us. He is a longtime friend and colleague. We've kind of interacted, I think, in many different ways, right, David?
I think so.
And yeah, and it's always great to uh, hear what he's up to and what he's doing and to learn from him. So I think we'll have a great presentation today. I will let him introduce himself. We're, as you know, kind of informal here. As Donna said, people are trickling in, I guess, a little bit more. Please use the Q&A feature and for questions, and we'll get to those. And David, did you want to answer questions as they go, or?
As we go, if we can make it more of a conversation, that's great.
Okay, perfect. So I'll kind of keep an eye on both the
Uh-huh.
chat and the Q&A, and then I'll just interrupt you if that's okay.
Sure.
Um, so again, think Donna put the link, the link to the YouTube channel in the chat. So check that out. Also, we have some, I think, kind of exciting things happening with seminars that we have planned for maybe the rest of August and September and October. We don't have plans finalized yet. We're still working on them, so I can't announce anything, but keep an eye out for that. You could join us on the meetup, our Govys meetup, to get the announcements that way. Let's see, what was the other thing I wanted to say? Oh, so this seminar is sponsored by several groups. One of them is our Govys, which is a group that's kind of sponsored, supported by the American Statistical Association and the R Consortium. Also, the JEDI Outreach Group, Justice, Equity, Diversity, and Inclusion Outreach Group. David's very involved in that, as Donna and I both are too. And also the American Statistical Association Data Science and AI Committee. Do I have that name right, Donna? I always think it's wrong, but anyway, Data
You
Science and
do.
AI Community. Oh, good. Oh, good. Mark's on here. Awesome. Okay. All right, so I'm going to be quiet and pass it on to David, and we'll see what he's going to tell us about bias in machine learning and AI. So thanks, David.
Thank you very much. Want to give a thank you for Wendy for asking me, for Donna and all she does for just so many things. Seems that Donna's everywhere, but most of all, I really want to express my appreciation for having the chance to present to our Govys. You guys, man, I do data for good analytics, but it'd go nowhere without the data. And so it's, Census Bureau of Labor Statistics. I had a chance to serve on their data user advisory committee for a few years. Bureau of Economic Analysis. Sorry not to mention everybody, but go down the list. You are the guys who will make all of this work possible. It would simply not exist without your hard work, without your support. That's the good data. Today we're going to talk about good data gone bad and some of the things that can go wrong along the way. So let's dive into that. So there's the title, there's a bit of background information, a little bit of background on myself real quick. Grafham Analytics is an independent analytic consulting agency. It's like a micro a Westat or RAND. We're based in Southeast Michigan, sort of splitting our time between Ann Arbor and Detroit. I do a lot of work working on the local electrical grid using physics-informed AI. Also manage an NGO called Peacework, which does data for good work. And this is mostly from Peacework that we're seeing from today. So here's the basic story, that we had such high hopes for machine learning, for algorithms. If we could take out the human element, wouldn't it make things so much better? we had such high hopes for machine learning that in particular not only would it advance the science and make predictions better, make them more accurate, allow us to understand more deeply, but also that the applications had the possibility of taking the human biases out of the picture. And to make things more fair, if it could be done by machines without human biases, that hasn't always been the case. It's often not been the case. So what we're going to be looking at is why that happened, what went wrong, and how we can address it. And in particular, the key feature in this is not, we're going to be talking about broadly sources of bias. I think folks will be familiar with some of those, but give some instances of how that comes about, in particular, how the AI gets from people's personal biases, how that gets inside of the code to affect our results. How does that process work? So we can interdict that process. And so we're going to talk about sources. We're going to talk about appropriate ways to measure bias, and then talk about a process for designing against it. So rather than being reactive, so often what we do, oh, we have an algorithm, oh, it's got this problem, we have to fix it. Or, maybe in a good case, we're testing this algorithm and it has this problem, maybe we shouldn't release it. But what I want to promote especially is a design approach, to be aware of the risk of bias from the outset. And in the conception and design for projects, understand that we're going to be looking for bias. We're basically going to assume that some bias is present. We have our own biases. We have to make sure that those don't get into our analytic products as much as is possible. And so we can design against bias. And that approach of mitigating, minimizing bias by design is the real focus of what we've got here. We're going to have some good R code for measuring it. And well, let's dive into that. Give a couple of examples. Selection bias. I think we're familiar with the concept, but here you can see not only a problem. This is Alex Njibi's work. He's out of Harvard. When he did this, he was a postdoc. I don't know if he's got the PhD yet. Really, really important work. He looked at facial recognition technology, found out that you'll notice there are some major players here on this. Sorry, this slide is too busy. But you'll notice that darker skinned females have a much lower rate of accuracy, of recognition than other folk, that women are a disadvantage, darker complexion is a disadvantage, people with both are at a very marked disadvantage. And so this bias that it comes from selection, women are still holding up half the sky, but if they're just not well represented in the data set, if persons of color or whatever it is you're trying to measure, if you want to do some particular group, LGBTQ plus, for example, if they're 8% of the population, don't hold me to that. Just give me an example. It isn't 80% of the population is what I'm saying. If it's an underrepresented group, we're going to make sure that they're properly represented in the training set. This is how disparities in the population, which are just natural, can get into the code and into the training when we don't properly represent them in our training set. So we train the data, we train the algorithm on biased data. And here's what you get. You get a bias trained population. Guess what? You're going to get biased results. But look at the results that we're seeing. What's the consequence here? Here we go. Okay, facial recognition, it's biased. But there's this project called Project Greenlight. It's traffic stoplight cameras. They do facial recognition. They find people who are like running red lights and stuff. But you'll notice where they're located in the city of Detroit, which is my hometown and live just a few miles away. I work for the electric company based in Detroit now. You'll notice that there's a match between in the graph in the middle of the page, you've got where these surveillance cameras are, and they're not always very accurate. They especially have accuracy with certain well-defined subsets of the population. And yet those very same traffic light cams right in the middle, Project Greenlight Detroit, funny how they match up with the Census Bureau demographic. I wonder how that happened. And so now not only do we have an AI that wasn't built as well as it could, but what we have are disparate impact in policing. We have over policing of minority disadvantaged populations as a result of bias getting into the AI. And how it got into the AI was a bias training set. Here's another thing. Now, if you look at the literature on this, this is an informal group. This is not a talking to university stats department, but I do want to mention, if you look up this problem, you will not find it under this name. If you look in literature, it's going to call prejudice bias, but it's something that's broader than prejudice. It's something that happens in the instances where human prejudice isn't an issue. Let me talk about what the key problem is. It's when we train machine learning based on labeled data that are labeled by previous human decisions. And the result of this is we are training the algorithm to simply repeat what people do. Now, the example given here, let's say we're doing resume screening. And we're looking for the best resumes. Well, if the ones that are flagged as yeses are the ones that people decided on to hire or move forward in an interview or give a second interview, something like that, current employees, and you decided to promote them as opposed to not promote them, if the yeses and the nos in the labeling of the training set are based on human decisions, the only thing you're doing is teaching the AI to recreate human bias. So instead of removing bias, it inculcates it even deeper into the system. I do call it history problem. I'll give you another example. It doesn't have to involve prejudice. For example, let's suppose in manufacturing, you wanted to identify parts coming off an assembly line. You take a bunch of pictures, boom, 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 put it in a photo booth, and then you run through the same sort of systems you got, like for cancer screening and MRIs and for the brain and things like this. They got them for manufacturing too, and the idea is you're supposed to find defects in the manufactured item, and you're writing AI to look through these images and find defects. But if the labeled training set were only things that the human inspectors found in the past, then the only thing the AI will ever catch are things that human inspectors found in the past, and it won't be any better than people doing the same job. You can train the AI by to simply recreate human bias. Now, that's why I call it the history problem. You could be using some sort of image recognition system, and you're trying to find out which one of 42 flippin' wood warblers in North America happen to be nesting on this particular site or in this migration pattern. But if you only use human identification for the labeled data, you're still going to get the same birds wrong that the people did. So when we talk about the design process, part of the design process here is having an independent, disinterested, not having any interest in the outcome, having a disinterested group of people look through the data, relabel the training data. Again, with people not having an investment in the outcome, have them relabel the training, not past human decisions, but a new unbiased, as much as you can make it. Bias can never be completely eliminated, but we're going to work to minimize it, shrink it as much as we can. We're not talking about bias elimination. Sorry, that's off the table. We're going to talk about bias mitigation as much as we can do for that. And so by having an independent group of folks, not investing in the outcome, relabel the data, yes and no. It could be cancer, it could be who gets a loan and who doesn't, whose resume gets sent to HR or not, whatever it is. Having the data relabeled by an independent, disinterested group is going to give you an unbiased input training set, and then you're going to get a better algorithm. This is what we mean by a design approach. We make changes in how we approach the process of creating and training AI, and it results in a mitigation of bias. Spaghetti problem. In this case, there's a little bit of a joke over here. For old folks like me, you've seen libraries that once upon a time that had dictionaries that were 6 inches thick. Here I'm making a joke that it's a data dictionary. The point is, if your data dictionary has thousands and thousands of possible predictors, Most regression models, you don't have 8,000 predictors, but more and more and more, we were doing text analytics, and it's not only text, it's a few other things. I'll tell you, and I'm sure there's a few of them on this meeting today, folks who are dealing with DNA. I don't know. My PhD is just in astrophysics. I am nothing like these DNA guys. They're trying to find out evidence of a broken gene amongst 40,000 possibilities, and they got 40 cases. And how they do that, I don't know, but they do an amazing job. So my hats off to them. It's not only text, though it's often text that manifests itself. DNA testing is a special case, but in any instance where there are many different training, different possible predictors, and then the model gets trained uncritically. Quote, anything that sticks is why I call it the spaghetti problem. The idea being, you might have heard the old saw that if you throw spaghetti at a wall and it sticks, it's done. Spaghetti experts, I know, I'm related to a few, tell me the pasta is actually overcooked if it does that. But anyway, the old saying is, if it throws at a wall and it sticks, it's good. Well, that's not good for training algorithms. We want to, once we screen it to find predictors that might be predictive, we might want to look at individual predictors to see if they inculcate bias. Give 2 examples. Let's suppose we've got an algorithm and it's going to predict the chance of recidivism, the chance that someone who has committed a crime or possibly has committed a crime might commit a crime again in the future, especially in the near future. And this is used for setting bail and parole and things like this. Let's suppose that one of your components predicting this is age at first arrest. Now, it turns out that if you're happen to be a BIPOC person, a person of color in some means, it's been found that very often you get a human bias. It's sometimes unconscious, but it's real. It happens. You get folks that you get into trouble in school, the police get called for one guy, they don't get called for the other kid. And often there's racial bias in this. And so age at first arrest becomes a biased predictor. You see, you need to look at the predictors and see, should we use this? Not anything that sticks. That's the spaghetti problem. You want to look at individual predictors and test them for bias. Give you another example. There was a company, fairly well-known company. You would think they would know better. They had this great idea for they were going to write this algorithm to screen resumes. They're a tech company. They're supposed to write really good algorithms, but they made a mistake on this one. It came out ahead in the end. But it's a sad story with a happy ending anyway. The company is Amazon, and at least according to investigative reports, here's what happened. They wrote an algorithm that was going to screen resumes. They were going to take like the top 5% or something like that. Take the 5% of resume, toss the rest, and everything would be great. They were concerned about being biased against women. They had a problem with women hiring and promotion. So they wrote a new algorithm to screen resumes. They tested that algorithm. They found it was biased against women, and so they did not deploy it. So a sad story with a happy ending. It talks about so many elements of right process. One, Amazon was assuming the bias was already present. They wanted to come up with an algorithm that eliminated a known existing concern of bias. They made a mistake on the spaghetti problem. They used any predictor that text analytics came out of this. But when they tested it for bias, and it was in alpha testing, they found it was at risk of bias, and they did not deploy it. Now, what kind of bias are you looking at? They didn't screen the predictors. For example, in their particular algorithm, remember, lots and lots, imagine all the different kinds of words that can show up on a resume. But it turns out that in this particular algorithm, as is reported from investigative reporting, the references are at the end. If the word softball appeared in your resume, you lost points in the algorithm. How many men play softball in college? How many women play softball in college? It can be nearly invisible. But when we look at the individual predictors, even if there's a lot of them, when we get this Rashomon set of these predictors that seem to be pointing in this right direction, we can screen individual predictors for risk of bias, like that age at first arrest, that can be racially biased. You look at softball in a resume, well, a whole lot more women than men play softball. And so we look at individual predictors in text analytics, in DNA research, and some people are more susceptible to presentation of a particular concern. So when we screen for individual predictor, we make that part of the process. Then we're avoiding minimizing bias by design. So how do we measure it? We talk about, okay, you want to set out with the concept that bias is a real risk. It might happen. It's a concern. We're going to measure. How do we measure it? We're going to measure it using disparate impact. Now, one of the really cool things is that this is all settled science. We know how to do this. If you look at public health studies, you look at so many other different kinds of things. Here's an example. In this case, we've got the first initial wave of COVID. And we're looking at mortality. We looked at mortality instead of disease reporting or hospitalization because deaths don't get missed very much. And so it's more accurate than whether or not somebody got sick and reported or went to the hospital. Well, in this particular case, we took all of the counties in the US, we divided them into quintiles by BIPOC, and we got a difference in mortality rate. Now, there are other confounding factors here you'd want to adjust for, of course. But the point is, the standard kind of public health study that we've done all along, we can treat bias as the disease. Bias, honestly, is a disease. We can treat it as one. And the science that we've been using all along in public health studies to find disparate impact. What communities have most lead in the water? What particular set of risk factors are there for opiate addiction, and on and on. All of these different things that we already know how to do, we can treat bias the same way. And this is how we can measure bias, treat bias as the disease. We know how to do the math for that already. So by measuring disparate impact using standard tried and true methods, you can measure disparate impact on disadvantaged subpopulation groups and measure the amount of bias and seek to minimize it. I'll give you an example. Cognitive tests. There's a cognitive test. We want to know if this particular test is biased. We're going to look at some R code here now. In this particular case, we're looking at this particular. You can look at the disparate impact.csv. It's male and female, pass and fail. You can get this on a GitHub site. The site is there. Thank you. David Coughlin and his for putting this on his GitHub site. This is shareable through Creative Commons license, giving credit, of course, to Coughlin, who put this all together. But it's simply a list. I think it's synthetic data, but not an actual test, but male and female, pass and fail on this test. And you want to find out, is there bias? So first what are we going to do? We're going to read the data in. We're going to look at the data a couple of different ways. We're going to do a crosstab. So here we actually create an object for the crosstab so we can print it out. We're going to create an object for the crosstab. Crosstab is gender plus cognitive test data is the disparate impact data set that we just read in. And so we get this, with 2 by 2. This is a simple example, but here we have the yeses and nos. In this case, it's cognitive test pass fail. It could be other things. Did you get the loan or not? Did we send your resume to HR or not? So many different things. There's still a yes and a no. One's good. Did you get bail or not? It could be a good thing, could be a bad thing. Did you finish your PhD inside of 4? Does anybody finish a PhD inside of 4 years? Okay, fine. You finish your PhD inside of 6 years. Great. At least it'll give some numbers on both sides. There's a yes and a no, and then you have those are the columns, the yeses and the nos. Could be a good thing, could be a bad thing. Testing positive for COVID is a bad thing. Getting the loan is a good thing. can be yeses, but there's always yeses and nos, and then you've got one row for each class. Now I only have two classes here. I got male and female. I could have 8 different classes. I could have a lot of different classes. There's a row for each class. In this particular crosstab, it's just 2 by 2, but it could be yeses and nos by every one of a large number of classes. We're used to looking at data this way. Here's some R code to do that. We'll want to take this a step further. There's something called a 4/5 test. And what it says, this is a test that's been used in a lot of places as an employment standard. So it may not be the particular test that you want to have. You know, just for example, you know, we all understand that p-values, they're not worthless. They're just not one size fits all. You know, p-value equals 0.05 works pretty good for medical stuff. If you were trying to get something where there's not so much at stake, if you want to get just general, you know, is this particular curriculum, do you do better on the final than this other curriculum? Maybe you want to go with a p-value of 0.2. If it seems to work 4 out of 5 times, that would be something of an advice. Do I use this textbook or that textbook? Again, 0.05 is still used a lot for medical stuff. It has its risks. Would you really want to have a p-value of 0.05 for, say, testing a nuclear power plant? Because I know I would. Well, in the same way, want to have different standards for the amount, for the kind of particular question. Now, that 4/5 standard is very commonly used for hiring and employment. We want to make sure that we use it at an appropriate level. Let me talk about the 4/5 standard and what it looks like. If there's disparate impact of more than 20%, if a disadvantaged group is at 4/5 or less of than the advantaged group, then we would say that bias is present. This is often used as a standard in hiring. We can move those numbers up and down depending on how much data we have, the quality of the data, and the criticality of the decision. 4/5 standard is a very widely used standard. It's like a p-value is 0.05. It doesn't fit all situations, but it's one we're going to describe here to describe the process. So we've got this crosstab, but let's go into this a little bit more deeply. We want to measure disparate impact to see if there's bias. So first thing we're going to do is from that crosstab, remember how we created it as an object? And we can pluck out individual elements. We didn't just print it, we created it as an object. So in R, we're going to pull out all the different elements, the 1, 1, the 1, 2, the 2, 1, the 2, 2. We're going to pull out all those different elements. We're going to count the totals, the positive for class 1, the negative for class 1. Yeah, put those together. That's the number, the total number of that population in class 1. And we're going to do that for every class. So here's some R code that you can use to implement that. We go on to the next slide. And now we're going to calculate something called an impact ratio. So we're going to look at the acceptance rate or the plus rate, or they got it or didn't get it. Maybe that's a bad thing like tested for COVID. Maybe it's a good thing like we're going to send the resume on to somebody else. But in either case, it's a yes-no acceptance rejection kind of thing. So in this case, we're going to do it for class 1. We're going to do it for class 2. You'll remember in the example we're giving, men are class 1, women are class 2. But it could be anything that breaks down into classes. It could be age or, you know, geography or other things. So many other things. Obviously, other Census Bureau demographics. The way I wrote the code is to make it more generic. So we've got really one for each class, whatever those classes happen to be. In this case, the potentially favored class, the privileged class, we made them number 1. And we're going to see if number 2 has an acceptance rate equal to or less than 4/5 the acceptance rate, or the yes rate, the positive rate of the potentially privileged class. So in this particular case, for this particular data set, we get an impact ratio of 0.84. That's greater than 0.8. It does not support a finding of bias. Notice how I've worded that. I've hedged this language. This language actually comes from my own work as a statistical expert witness in racial profiling cases. I don't want to say bias, yes, no. some bias is always present. How much is too much? In this case, we have a standard. And what we talk about is whether or not the data support a statistical finding of bias. I was literally asked on the witness stand one time last year in a racial profiling case, are you saying these people are racist? My answer was, this is not a statistical finding. I didn't say yes. I didn't say no. I said it wasn't a statistical result in the test that I ran in this particular case. So in this case, it's higher than 0.8, so it does not support a finding of bias. Now, how many folks are we going to look? 3, 4, 5? One would hope more than that. So in this case, there's a sensitivity test called an adjusted impact ratio. What we're going to do is we're going to redo the impact ratio. We're going to add 1 to the number. We're going to take that number in the positive class, add 1. We're going to take the number in the positive class. We're going to subtract 1. We're going to find that ratio. And what it gives us is a statistical sensitivity test. So we can look at the impact ratio. If that adjusted impact ratio is greater than 1, that also does not support a finding of bias. So we can use these impact ratios. This is just standard kind of stuff that's been used in a lot of situations, but it gives us a rule of thumb that we can use. This works for employment situations. You might want to move that ratio up and down. Is 0.8 the right number for you? Like p-values, find the number that's right for you and make sure that the people you're working with understand why that number was chosen. So summarize is actually a very, very long summary slide, and then we'll have a chance for some questions. Summary practices to minimize bias. The most important thing in this slide is not any one of these points, is that we're minimizing bias. We can't completely eliminate bias, but we're going to do our best we can to eliminate it. These are some things to consider. This is what we mean by a design approach. We're talking about a methodology that emphasizes this approach for writing algorithms in the first place. So at the back end, when you're done and ready to test and then deploy, you've done what you can to minimize the amount of bias present. There's some things in here that I haven't talked about in this particular examples. They don't translate to our code exactly, so we're going to talk to them in a little bit more detail. Number 1, parsimonious models. Models with fewer moving parts. Models that are simpler, are simply going to have fewer concerns. If you're sort of like scratching your head, should I really, really include this factor or not? Remember that the potential for bias is present in every regressor, every predictor, every factor, every feature. If we add more and more features, we might be apple polishing. It's not really making the model any better. Now, I work in industry. My background is in pure science, but my background is in industry. I'm going to describe it this way. Now, scientists will say that 2 numbers that are within a tolerance for error, you can't really be sure they aren't the same number. I'm going to describe that a little bit differently for applied statistics. I'm going to say that any decision, any difference in numbers smaller than a business decision is not a difference. If someone will not decide differently, hire, not hire, treat, not treat, go on down the line, whatever you're interested in, someone will take or not take an action based on that number, that difference is important. If the difference is too small for a person to change their behavior in response, it's not a difference. So parsimonious models means we're going to take out of the model any feature that isn't going to contribute enough to make a business decision, because every feature has some risk of bias. So we can, by design, mitigate the amount of bias, reduce the amount of risk of bias by only putting in features that we know are needed to make the decision that's going to be made as a result of the model or algorithm. Screen all predictors for bias, we talked about that. That's the spaghetti problem. Transparent methods, not black box. If you're familiar with the work of Cynthia Rudin, who's done some really, really important work in this, she will argue that there's almost never, at least in her experience, never found, in my own experience, never found, her experience is a lot wider than mine, and a lot more expert. But it seems like you can always find some model that predicts as well or nearly as well that's explainable, rather than, now I'm not down on neural nets, I use them myself, but transparent methods when you're making high value decisions, you need to be able to explain the results. And so one
Hey,
of the things we can do, yes.
I'm sorry, David. I don't know. As soon as you're done with your thought, we have a question for you.
Let me just wrapping this up real quick. So where we can, if that neural net or other black box method gives us a much better result, that's going to be very persuasive. If it's not improving the decision making, then we're going to tend to decide against black box and in favor of more explainable models, just as a rule of best practice. What's the question?
Okay, thanks. I think this is regarding number one, parsimonious
Yeah.
models. Can't some features counteract the bias of others?
The approach that I've taken is looking at individual features. You can certainly look at features combined. Again, the way we're going to measure bias is by disparate impact. We talked about the math for doing that. You can have a look at some features. If that's something you're finding, I would certainly be interested in looking at that. If you find
Okay,
that one feature counteracts bias. I tend to think of bias as a feature by feature kind of thing. But if you're getting the proof is always in the pudding. As George Box famously said, all models are wrong, but some are useful. If your model is more useful because of the inclusion of a feature, if you're making less biased business decisions or diagnosis decisions or guidance for your project, then yes, include that feature.
yeah, and I'll just say that this is one of my pet peeves, I guess, which is that we should always be trying to have parsimonious models. Wait, we have another question too. In the previous example, we were on the lookout for bias against BIPOC. In the next example, we were on the lookout for bias against women. How do we determine what groups we need to be on the lookout for? Good question.
That's a fabulous question.
Yeah. And then how do we avoid falling into the habit of only checking against the things that we know to check for?
There in terms of process, there are a couple of things. Now, my personal experience, you can write this down as Corliss's law. Ha ha ha, that's a joke. If there's a social problem out there, pick one. Doesn't matter one. Well, I earned this gray hair. I've been doing this for a little while. If there's a problem out there, Black folks are getting hurt worse. Something to watch for anyway. So there are some traditional groups that we're going to look at. We're going to look at gender. We should be looking at age. I think that often gets overlooked. We need to be looking at LGBTQ plus status if that information is available. There are some folks that, you can have a serious bias in the data because some folks don't want to share that information. And so that brings us into the other side. It isn't just enough to measure for every group that you can think of. What you need to do is incorporate in the design process people that aren't part of your project, don't have an investment in the outcome, and listen to their suggestions. Who should we be looking for? Ask genuinely. Ask, are you aware of instances of bias that we aren't aware of? Because, of course, one of our own biases is a cognitive bias. We don't know the things that we don't know. We aren't going to suddenly start seeing the things that we have always overlooked. So if people who wear blue shirts are a marginalized group, how are we going to know? We're going to find out because we've got somebody else on the team not invested in the outcome will say, watch out for this. It's how you build your team and have people warn you, have that open table and sharing around the table of things to watch out for. We're all going to be reading journals. We're all going to be, going to conferences, picking up on the latest research, watching webinars. Get thoughts. What are the things we ought to be measuring? And if something comes up later on, then immediately that you hadn't thought of before, go out and measure it. But start with assembling a diverse and equitable team. It starts with diversity on the team, and that leads to better performing algorithms.
That's a really good point. Thanks, David. We have another question in the chat. In the disparate impact example,
Yep.
Might you want to control for other covariates before measuring disparate impact?
Absolutely, 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 100% right. I couldn't agree more. This absolutely needs to be done. We've got an hour here. And so I wanted to go through the methods for the measurement, but absolutely. Say that, ask that, please read that question again. It's something all of us need to take to heart. Wendy, let's have that again, please.
Yeah, in the disparate impact example, might you want to control for other covariates before measuring disparate impact? And then there's this following statement. Otherwise, any disparate impact might be the effect of some other factor not under investigation.
Absolutely true. Absolutely needs to be done. I focused on how to measure things in this short talk, but it's absolutely something all of us need to take to heart. Thank you.
Perfect. That's it.
Okay. Going down the list, we talked about transparent methods, not black box. How to label your training set. We talked about it in that detail. Couple words of advice. These aren't requirements, but I found that these things are useful. Test for bias measured by measuring disparate impact. We already know how to do that. We gave some examples, we gave some code here. We also gave, just there's a whole lot of studies out there that already measure disparate impact. The particular thing you are looking at may not be in any of those studies, but the math, the mathematical statistics behind this measurement. This is a very, very tried and true set of tools. And that we can find stuff that's in print, widely cited, widely accepted, that shows the steps in mathematical statistics for measuring disparate impact. Odds ratios or relative risk. This is a really good word of advice from Lance Heilbrunn, who's a mentor of mine, worked at largely cancer researcher, but a statistician working at Henry Ford Hospital in Detroit for many years. When I first gave this talk, or a proto version of this talk, a long time ago, he had said that he had found in his experience odds ratios or relative risk. They work really, really well for people who aren't statisticians. So often our decision makers are themselves not scientists. They could be policymakers. They could be people in government. They could be people in industry who may not have that particular background and training. Or they could just be people they were trying to recruit support. In some cases, they might be people that are candidate for voters, or writing a letter to the editor, or something for the general public. Odds ratios and relative risk are things that the general public gets their arms around a lot better than the kind of statistical language most statisticians speak most of the time. So instead of saying, we've got a mean value and here's our confidence interval at this percentage rate, you lose people, at least in the general public. When you say that, what we found in our scientific study is that they got 60% more chance of this bad thing, this good thing, whichever, if they have this particular characteristic. Men have a 30% chance more likely to get their resume moved forward. Persons in this particular demographic have a 4 times higher chance of actually dying of COVID should they actually get COVID, which is one that we had seen before in an earlier slide. Expressing things in relative risk and odds ratios is something that, in my experience, the general public really can get their hands around. This was pointed out to me by Lance Heilbrunn, as Dr. Heilbrunn recommended that I mention this, that this is one of the best ways to get that message across to a general, especially a non-statistical audience. And then the last point, I'm recommending this as best practice wherever possible, open source data and algorithm. Now, there are times when we can't open source stuff. So how do we open source stuff when we can't open source? And here's what I mean by that. Maybe it's proprietary information. Maybe it's something that you just can't open source. Like, how are we detecting whether or not there are missiles coming over the North Pole? We probably don't want to open source that algorithm, even if we could. So what you do is you bring in an outside, again, it goes to this design approach. you find an outside group, they're the same agency, they have the same security clearance. They could look at the data, they're working on a different project, and they're not investing in your project. Have them review the algorithm and get their thoughts. When it's all done and ready to deliver, get an outside group of people, even if it has to be inside your company, inside your agency, inside your own group of people, inside the same social services network. You know, for example, I write algorithms that I identify risk of being victims of human trafficking. We can't share this kind of information with just anybody, but we can find people within our own particular group that have access to the source data. They just aren't working on that particular project. And they can do a sort of inside open source. That is, they have an independent review from people who can do the statistics, have legitimate access to the data, but don't have an interest in the outcome. Have them review your stuff and test it for bias. If you can't actually open source it, find another group that can do an independent review. Okay, so that's my to-do list for design methods for best practice. I got references, and we got more time for questions.
Yay, thank you. I don't see any other questions right now. But if folks want to put something in the chat or the Q&A or raise your hand, then please do so.
Couple things real quick. If you have thoughts afterwards, let me know. You can get a hold of me at that email address. Check out our website if you like. Couple things while people are putting in questions. Yeah, it's August. He's getting later in August. The deadline for JSM for next year is like September 5th. So there are a lot of conversation going around the statistical community about making sure that people get their best new work on display. You got to plan in advance for these things. The deadline for invited presentation for next August, that's in Nashville, right? Is coming up faster than you think. Now is the time to be working on proposals for next year. So there's a plug for American Statistical Association, all the other wonderful groups that are involved in JSM.
Yeah, good point. And there's also other conferences that might intrigue people, ASA ones. So the Women in Statistics and Data Science, that's coming up in October in Reston, Virginia.
That's just down the street from you guys, right?
Yeah, yeah. And then there's and I think we're having a short course on ethics, which is right along in keeping with this talk today. And then I think in April next year is the SDSS Symposium on Data Science and Statistics. So lots of other interesting opportunities. So keep an eye out there for them. And like I said, we'll have some other oh good, Mark said yes, September 5th is a deadline for invited session proposals for JSM. Nashville should be a cool place to go to.
They had a couple of near misses with Nashville with the Conference on Statistical Practice. They had to because of COVID. They were all set ready to go and dropped it because of COVID. So that was unfortunate. It's nice that we're going to Nashville.
Yeah, see, it seems like the JSM's been going to sort of some non-standard cities lately.
Yeah, yeah. This is the first JSM I'm actually going to get to drive to. I'm in Ann Arbor, Michigan. So
cool. Hey, thanks, David. We had a question.
Yeah.
Somebody asked if you could show the reference page.
Oh, I'm sorry. Of course.
Yeah. Perfect. And like I said, I will send out the slides, but just in case if I'm, delaying or something, if you'd like to email me, let me put that in the chat. I'll put my email there. So it's wendy.l.martinez@census.gov. I can email the slides to you. And okay, let's see. I'm trying to think if there was something else I was going to mention. Well, if there was, I'm forgetting it right now. Yeah, so yes, my plan is to drive to Nashville if I can make it next year. That would be great. So you're gonna drive too, David?
Yes.
Yeah. All right. Well, thank you. And yeah, we have somebody who's a colleague who has family that goes to Nashville. I don't think I've ever been there. So it'll be interesting to see that city. All right. Well, thank you, everybody. Stay tuned. Keep an eye out for other events that we have going on. And oh, good. There's Richard who thanked you for a good talk. And great. Well, thank you so much, David. And hopefully this has inspired people. Yeah, I'm kind of intrigued. I'm sorry, we were saying goodbye, but one thing that sort of intrigued me was
Mhm.
this idea of maybe that looking at the different predictors in a multivariate way would be useful.
Definitely something to look at.
Yeah. All right, food for thought. All right, well, thanks again, David, and
Thank you very much
looking
for having
forward
me.
to seeing you whenever I can get to a conference. The one that you're at too.
Well, yeah, let me see. I'll be in uh, NASA JPL Pasadena next week. But I'm going to talk about how we use satellite data to give fast responses to power outages. So I don't know if any of you will be there. I'll be in Oklahoma City in 2-3 weeks to talk about counterterrorism with the Society for Terrorism Research. Talk about stochastic terrorism. So
Oh, wow, that's
those are
interesting.
the things that I have coming up.
Well, you're getting a whole lot of thank yous, so there you go. All right, well, thank you, David. I won't be getting to any of those places, but sounds like it'll be a lot of fun. All right, well, take care. Thanks, everybody, and hopefully you will join us at our next Govys. All right, take care. Thanks, David.
Thanks.
All
Bye-bye.
right, bye.